All right, so I have been having a ton of fun recently playing around with the GPT speedrun projects like modded-nanoGPT and now nanochat. And I've been doing a lot of just logging stuff and then looking at trace files and looking for opportunities to improve things and then making pretty illustrations like this one. So I've been asked a number of times now if I do a tutorial to kind of show my process for this, show how I make them. And really what it is we're using the PyTorch Profiler to create these trace files. They're in a Chrome trace format. I guess the format was invented for debugging browser performance. And there's a tool that I use, website ui.profetto.dev. And this thing is great. And it's what makes the pretty plots for me. And then I'm doing it in PowerPoint after that. But let me show you how to create these, and then I'll show you how to read them. I'll show you how to kind of navigate through the model and look at the kernels in there. Okay, let's take a look at the code. We don't need to look at the code much. It's not actually all that interesting, and probably makes sense to look at it more statically. I think the video, it'll be fun to look at the actual profiler tool. Actually running what should be a record run right now. I'm actually on a spot instance, so kind of rolling the dice here a bit. Hopefully it completes. But we'll be looking in this video at a change I was able to make, kind of a GPU optimization that decreased step time. So I'll show you the work that I've been doing this morning to figure that out. The profiler code, I kind of just bolted on when I want to do it. So it's not something I really have integrated into my training scripts. So I'll just pull up a file that has it and diff them like this, right? And just kind of copy over the changes. But yeah, you set up a profiler and do a small, you measure a pretty small number of steps. These trace files are big. They're like 15 megabytes maybe, uncompressed. And yeah, so a few steps is enough because really you only need to look at a couple at most. So wait some, do some warm up. I don't know what warm up does. Yeah, I'm going into too much detail, but you can see it's bolted on. Like I cut out the training loop and just put in 4 profiled steps, 14. Okay, I'll try and share some better example code than that. Sorry. But let's just get to the fun part. So once you've got your trace file from doing a run, you head to the site, open trace file. Let's see which one I want here. Yeah, here's our record right here. Rope chunk. Open it, and you'll see something like this. So what's going on here is we've got on the top row, this is Python. This is the stuff running on the CPU, all the Python functions. I don't look at those all that much. This is kind of where the magic's at. This is, it's always 0. These are all the GPU kernels. Yeah, it's kind of a fun way to get a sense for where all of the compute goes during training. It all kind of depends on the model size and the batch size, but it gives you some idea. So for sure, the backward pass is like the most expensive piece between forward, backward, and optimization. Backward's the big one. And then the optimizer is comparatively pretty small. And then something I like has been really fascinating to me to see. This is especially prominent when you look at a much smaller model, like a 12-layer model. This whole thing right here, that's the language modeling head. And then this is backprop on the language modeling head. And if you look at that in like modded-nanoGPT, which is 12 layers, like it's an impressive percentage of the entire operation is just that part. So even here, that's like, what is it? It's like a 650 millisecond step. 18 milliseconds of that is just the LM head. Not counting the optimization for it, which isn't that much. But let's start by diving in on the optimizer. This is actually where I've been making almost all of my contributions. my favorite place to be right now on this plot. It's the optimizer. Really, this deserves its own video because there's lots to talk about here, but I'll try to be quick and just give us a brief overview here. Just go left to right. So this is the end of the backward pass, and then this right here, all of these guys, all these kernels, are gradient accumulation kernels. So because we have a gradient accumulation step, the first time PyTorch is able to calculate the gradient and store it directly into whatever matrix buffer it's keeping it in. But when you do another step, it's got to do one of these element-wise operations to sum the new gradients with the old ones. So kind of paying a penalty here. And if you could get this to run in just a single step, you could get this to go away. That'd be a good win. And then this is fun. So these tiny little slivers here, these are Atom. That's the Atom optimizer, fused Atom, probably running on something really big, like an embedding table. You know, like a huge number of parameters being optimized in like 30, 40 microseconds. And then over here, this is Muon. So this is Muon run on the attention matrices. And Muon has got, it does like orthogonal, it orthogonalizes the updates, and it does that with this kind of iterative matrix multiplication process where it does 5 iterations of the polar express algorithm. So these are all big matrix multiplications, and you can kind of see, you can see the 5 iterations just visually, right? So that's kind of a nice thing with these plots is it's very like, they're very pretty, and there's clear visual patterns that you can become familiar with. Yeah, and then, right, these are some big mem copies related to preparing the gradients to transmit around. And then these are mem copies back out. And then on the communication bar here, these are all reduce scatter operations. So that's where the GPUs are sending each other the gradients that they have. And then these are the all gather operations, where after each GPU has done its part of the optimization work, they're exchanging the updated weights. Okay, that's it for the optimizer for now. Can't wait to come back to that and go into it more, but let's look at a bit of the forward and backward pass, and we can start looking at what I was working on this morning. So if you zoom in on the forward pass, zoom out a little bit, and you can kind of see a repeated pattern, right? So we've got 24 layers, so there should be 24 of these kind of repeat patterns of execution. And the way I'd like to navigate through this part of the code is to find FlashAttention. It's always its own kernel, and it's going to be a different color, so it stands out. So there it is. You can see FlashAttention there in the name, right? Just find the word flash, and that's good. That's enough. So now we've got the FlashAttention step, and we can look for the next FlashAttention. So there we go. So now we've got one layer starting from, like FlashAttention all the way to the next FlashAttention call. So we're kind of like straddling 2 layers, but it's the easiest way I've found to navigate. So right after FlashAttention comes the output projection for attention. And then when you look at these kernels, the PyTorch compiler is fusing lots of operations together. So they've got these great names: unsafe view, add, mean, multiply, power, root square. But yeah, you can look at that and kind of infer the math, right? So the RMSNorm happens in a few different places. So anytime you see multiply, power, r square root, you know you're looking at an RMSNorm kernel. That's a good landmark as well, because that means that's the layer. It's the normalization going into the next step, which is the MLP. So these are the 2 big MLP matrix multiplications. And in general, NVJet, those are going to be the matrix multiplications. I think that's like Kublas. You know, I'm kind of out of my depth there in talking about those things. Then these like kernels that are named Triton, those are typically the element-wise operations. Yeah, so we've got another element-wise here, which again, you can see ReLU in there. So that's the activation between the two, between the input and the output MLP matrices. Okay, I've got to give you some context for this next part. So in modded-nanoGPT, it's all about the benchmark, and it's kind of anything goes. If you can beat the time, then more or less that's a record, and whatever convoluted solution you've got, you know, it can be considered. nanochat, on the other hand, part of the philosophy, the goal is for it to remain elegant, for it to be a good teaching tool, a good starting point for other research work. So not every optimization is allowed in there. So I've got my own little like modded nanochat repo going where I'm putting in like all of the optimizations that we know work, but are just maybe a little too complicated to belong in the proper nanochat. So kind of where I thought I'd start, maybe one of the most obvious ones, I suppose, is like fusing the query key and value projections. So those all need to happen at the same time. So why not just put them in one matrix, make it one big matrix multiplication? And I did that, and it didn't give the speed up that I was expecting. So a great thing about these trace files is that you can implement something that you feel like should work, and then it doesn't, and then now you have a way to go figure out why. You know, it's not just like, oh well, I'll move on, try something else. Like you can actually dig into it. Let's go look at the actual trace files and see what happened, why it wasn't as fast as I hoped. So on the top here is the baseline, and we can see we've got our 3 QKV kernels, and then a RMSNorm for the QK norm step, which you can see there's add, concatenate, mean, multiply, negative, power square root. Yeah, always lots of stuff fused together. Yeah, and then down here we've got our single QKV projection all in one kernel, and I don't know if the text is probably tiny, but it's 970 microseconds versus 873. So definitely a substantial improvement there. So great, cool, should be a win, right? But something else is going on, so got to keep digging. So this is the forward pass that we're looking at here. And the next place to look, sometimes it's the optimizer, but next place to look here would be the backward pass. We can see what kernels are being used there and see if there's a problem. So this, I zoomed out, I moved over to backwards. So that's the forward pass. We're just going to jump over to a backward pass. We'll just pick any old layer. So here we go. This is where we want to be. We want to know what happened here. How come I'm not winning? So 1.7 milliseconds. And then up here, kind of map out the same thing. That's backward, or the layer norm input. Gosh, sorry. Yep, and then that's 1.176. So big difference there. 0.6 milliseconds, a lot faster in the baseline. Yeah, so what's going on? That's where I typically turn to AI to kind of help me navigate this stuff. I tell it like, all right, this is what I'm looking at, this is what I'm seeing, and then this pops up at the bottom. So for every kernel, you can view the name, the duration, and then down here are the launch parameters. So this tells you kind of like how many threads and in what arrangement were used to run this kernel, as well as the number of registers used. Register pressure is a concept I don't, yeah. So again, like I don't totally know what I'm doing with this information, So that's where you just kind of like select all, right? And then copy and paste that into a chat with like GPT or whoever, and tell them like, what's the difference between these two kernels? What's going on? Why is this one so much slower? And they can read this nonsense and tell you what's up. And here in particular, it is the word cat right there. So what's happening is that the PyTorch needs to concatenate the query key and value gradients in order to update the one big QKVO fused matrix. So I wrestled a bunch with trying to figure out how to fix that issue. I knew it should be faster, and eventually had the sense to just compare what I was doing with the nanochat code to what's in modded-nanoGPT. And Claude pointed out the key difference was the use of the chunk operator. So applying that like fixed things, and then made me ask like, oh, hey, could we do the same thing to nanochat? And apparently, yes. So in the rope code, current baseline, we calculate half of the head dimension and then use a slicing operation to split up the two halves for rope. And if you switch to chunk, then the Torch compiler is able to do something better. So this is that chunk of code in backward. The baseline uses this single giant kernel, and with the chunk operator, it splits it into these pointwise ones. So 196 plus 140, so it's like 340 versus 570. Yeah, so that cut our step time down and got us a new nanochat record. Sweet. Okay, this is fun. The run is finishing up. So I did two things with it. I did the chunk change that we, it's a funny way to say it, that we've been looking at. And then I also, in modded-nanoGPT, I introduced a bug that turned out to help where I flipped a learning rate multiplier around on the MLP. It used to be like a 2x multiplier on the input matrix and then 1x on the output. And I made a change that flipped that around, and it improved loss. So I've applied that, curious to see if that's going to help here. And then, yeah, if it doesn't, I think that's okay, because I think we've beat the time. Does it have the total time here yet? I know it's going to report at the end. This is like, we need to hit, that's the core score we need to hit. And then training time record is 3.04 hours. And we did it in under 3. And then something kind of cool is I'm on a spot instance right now that costs $7.51 an hour. So we just trained this thing for $22.50. Pretty cool. So this is the pull request where that learning rate flip happened. And it was pretty interesting because the record is the light blue line. And it was actually like the validation loss was higher the whole time until we got to the very end. It beat it like at the very end of training. So it kind of suggests that maybe like the model with the original learning rate setup was overfitting a bit. And this helped address that. So I'm kind of hoping for the same thing here, get us a better score on the core metric. We shall see. Okay, so it turns out I've been sitting here waiting for this thing to finish, and I just needed to scroll down. But we did it. We beat it. Core metric 0.2633. So that is awesome. That means we should be able to remove some steps and get the training time down even more to hit the GPT-2 mark. So cool. Okay. Did not, in fact, get my name on the leaderboard with that run, so figured it was important to come back and explain what happened there. So first off, with that core metric score we got, 26.33. I know better than to get excited about a single result. If you look at modded-nanoGPT and our submissions to that speedrun, we usually have to run between like 6 to 10 times in order to demonstrate with confidence that our model has reached the required validation loss. Because you can just have a really lucky run, or you could have an unlucky one. So you need kind of a good sample to prove some statistical significance and confidence. And Karpathy said, many times now that the core metric is noisy. So it's kind of dangerous to look at, really, because you can get probably too discouraged or too excited based on your core score. And then the other thing that happened there, the post that I was referencing for the baseline did not have the validation bits per bytes in it. So we were just looking at this number, and I was excited because we came in at 26.33. But the validation loss is a much more stable figure, and mine was a lot higher than that. So where are we at? Yeah. So that's a better indicator of performance in this case. So yeah, model did not train as well. Okay, and then here's what happened with the chunk operator versus slicing. So at that same weekend that I was working on this stuff, Karpathy was getting 8-bit training to work. And when you enable 8-bit training, the whole kernel landscape changes dramatically. And now with that change, the chunk operator is actually slower. So, bummer. But I did want to show you something here that coming back to this made me realize, and I think it's a good insight to take away. We were looking at a single attention layer, right? And something that doesn't take into account is that not all of the attention layers in this model are the same. If you look at the configuration, there are long context versus short context attention layers. And then there's also these value embedding tables, which are added every other attention layer. So there's multiple multiple attention definitions going on here, and you kind of have to look at all of them, right, to make sure that whatever your change is, that it's improving over all of them. So the way you can kind of spot a set is if you notice these kind of, I'm so bad with color, call it turquoise or mint, I don't know. But you can see these flash kernels. These have got to be the long context ones, because in between each one of those is a short context, which is, where are you? There we are. Okay. Yeah, sorry, it's a little tough to see, but yeah. So there's three short context flash kernels and then a long context one. And same thing down here. And then that's also true in the, this is the backward pass, and forward pass shows the same thing. A little more zoomed in here. But yeah, so chunk in this context is a little slower, unfortunately. All right, thanks everyone.